Before we start talking about a regular polygon's area, let's recall what a regular polygon means, why it's special to be a regular polygon of any sort. A regular polygon has the following two properties. One, all sides are congruent. And two, which we're going to take advantage of both the first property and the second property here, which is that not only are all sides congruent, but all internal angles are congruent as well. Exterior angles, yes, the exterior angles need to be congruent to themselves as well. You could say that, however, I don't want to say all angles in general because an interior angle is not congruent to an exterior angle. So I don't want to just say blanket statement of angles. But interior angles are congruent. Exterior angles, as you've defined, are congruent to each other. That's true as well. But I don't want to. The important piece is the internal part for us when we're trying to find the area of a regular polygon. In addition, we're going to add a special segment, a vocab word here called an apophthegm. This segment is the perpendicular distance from the center of a regular polygon to any side. In the figure that's drawn in, segment FG is an apophthegm of this regular pentagon. It's perpendicular distance from the center to the side. Okay. Before we kind of jump into finding areas of these things, I want to kind of get a refresher of taking advantage of specifically this second idea that all internal angles are congruent, and look at, say, this hexagon that I've got drawn here, and finding some angle measures based off of this fact that all internal angles are congruent. So, for example, what's the angle measure of EGD in here? What's the angle measure of EGD? Well, how many sides are in this hexagon? There are 6 sides in this hexagon. So if we think of this hexagon as, say, how about we drew these diagonals? How many chunks are we going to, how many of these angles are we going to form by going from vertice to center to vertice? How many of these internal angles are there going to be? 6. And if they're all congruent, because it's a regular hexagon, what is any one going to be? What is the measure of any one of these internal angles going to be? If you add them all together, don't you get a full circle? If I added all of these pieces together, you get a circle. That's 360. So there's 6 of them, and out of 360, we should have, each of them should be exactly 60-degree wedges. Or if your polygon has n sides, each internal angle should be 360 over n for how many sides there are. If it's a 6-sided polygon, we'll do 360 over 6. If it's say a octagon, we can do 360 over 8. Would tell us any one internal angle in here. How about DGH? DGH. 30. It's got to be half of whatever one of them is. Again, because if we're drawing the apothem, it's perpendicular. Therefore, it's a perpendicular bisector of this isosceles triangle. It's also an angle bisector, which is good. We could show that. We could prove that if we wanted. GEH. GEH. How are we going to find what? Well, that formula, Alyssa, would find what, like AFE would be. But I just want to know what GEH. I want to know what this angle is. Okay, we've already found. We know this is 90. Ben. No, this is 30. The triangle, 90, 30, that means this left over, it's got to be 60 degrees. Oh, in this case, yeah, you get 30, 60, 90 triangles, so that makes life even easier down the line. FGD. FGD, then. FGD, that's 1, 2 of those chunks. They were each 60 degrees. Therefore, it should be, if there's two 60-degree chunks, it should have to be 120 degrees. Well, I want to be able to take this idea and come up with a way to actually calculate the area of any regular polygon. Our strategy is going to be this. If we take the polygon and from its center, we draw all the diagonal. We draw. I think of it as like a radius from the center to each vertex. Notice that we're going to create a bunch of triangles in here. Also note that since each of these degree measures is the same, this is a regular polygon, and this is based off the regular idea. Since this is a regular polygon, each of these sides are congruent. They have the same quote unquote radius here. They have the same side length here, so we have a bunch of congruent triangles. Namely, for every side, we're going to get one triangle. Do you agree? This hexagon, we have 6. If we did the same game and we did it with, say, a pentagon, a 5-sided figure, we get 5 triangles. Get it with a octagon, you get 8 triangles. If we could find the area, or come up with a formula for the area of any one of these triangles, and then multiply it by how many sides there are, or by how many little triangles we get, we'd come up with the area of this whole regular polygon. Okay, so we're going to try to find, our plan of attack here is find the area of one triangle, then multiply by the number of triangles. That's our game plan. Okay. What's the area formula for a triangle?
The one that base and type.
Wow.
I got it first.
I think Tyrus might have had it too.
Oh, Tyrus.
I
Just a little bit.
Oh.
So applying this game plan, if we take 1/2 base times height of one of these triangles, and then we multiply by how many sides there are, we should get the area formula for this polygon. Well, hold on. In terms of that new quantity of an apothem and a side, oh look, an apothem is the perpendicular distance from this vertex to the side. What's that also known as? Of this triangle, it's the height of this triangle. What's the base of the triangle then if this apothem is the height? The side. And what do we know about the side length of all regular polygons? They're the same. So if I could find, therefore, the area of one of those little triangles better be whatever the apothem is times the side length. So number of sides. So in parentheses here, I have the area of one of those little triangles. And if I multiply it by how many triangles we have, which is the same as the number of sides, I should get the whole area of this regular polygon. Another way to state this is, what if I, since I can multiply whatever order I want, what if I multiplied in this order? And we'll write this formula as well. This will be actually our second formula. The alternate way to write this is the following. What if instead of those parentheses here and here, instead of grouping it by area and number of sides, if I group it like this? What do you get when you multiply the length of one side by how many sides there are in this regular polygon? What's another term for this quantity? The length of one side times how many sides there are. The perimeter. So an equivalent way to write this same formula that we just wrote down is 1/2 times the length of an apothem times the perimeter of this regular polygon. These two formulas work identical. If you don't already have the perimeter calculated, then you could just take whatever one side is, multiply by how many sides there are, times the apothem times half. Area of a triangle times how many. Or you can do half of the apothem's length times the perimeter, gives you the same quantity. Okay? Either or works better. Well, however you want to use it, memorize it, do it, whatever. These two things both tell you the area of any regular polygon. So our goal now is for this section is to, if we can calculate what an apothem's length is, what the side length of our regular polygon, and if you can count on your fingers how many sides there are, then you can calculate the area of any regular polygon. Here's where we're headed with this, and I'm going to give you a bunch of examples of kind of if I go the easy route and I just tell you what some of these are. Or maybe as basic as if I just draw a regular polygon, and that's about it. You can still find the area. We'll talk about how we can use some things that we know to get there. Okay. So on the back, some examples. On the back, we'll start with a couple of relatively easy ones. And that if I want to find the area of these polygons, I need to know half of the apothem length times the side length times how many sides. I need to know those three things. If I know those three things, then I can find the area of this polygon, of this regular polygon. Well, let's see, do I know them? What do I know off the top for this first one? I certainly know the distance from the center to the side, that's called the apothem. Okay, do I know the length of one side yet? I know this distance is 8, but this is the side length. But we can find it though, and we'll find that in just a second. Do I know how many sides are in this polygon? We can count that. That's fine. So the only real calculation for this first example is the side length. I need to know what this length is right here. Well, as some of you noted, you can do that. If this is 6.5 and this is 8, then you could use Pythagorean theorem to calculate what half of the side length is. So you could say, like, what, 6.5 squared plus x squared is equal to 8 squared. I'm going to need someone with a calculator to play along here because I don't have one in front of me. So 6.5, someone please solve this Pythagorean theorem. 4.6. 4.6. So if x is 4.6, what's the length of the side? Hopefully, if we know that this piece is 4.6 and the whole length is double that, which would be 9.2. I'm going to go with 9.2 just because I rounded to 4.6. If I have this information, I know that this is the formula for the area of this regular polygon, plug and chug. So the area now, half times 6.5 times 9.2 times 5. And the area is that many square units, which someone calculated that for me, that would be easy. 6.5 times 9.2 times 5. Katie, what'd you get? Approximately 299.
I didn't do the half. What?
Did you multiply by half?
I got 149.5. Sorry.
Half of that,
Isn't that awesome?
149.1.
That is so fun. So fun.
Half of that would be approximately 149.5 square units. Again, I found these three pieces. I can plug it in. Please try B on your own right now. B is going to be almost identical to A. Please try B on your own right now. Okay, again, if we know these three pieces, the apothem length, the side length, and the number of sides, then we can calculate the area just by plugging into our formula. So in this one, just like the first example, the apothem length is given, 10 roots of 3. We don't know what a side length is, but we can count the number of sides to be 6. The side length, which some of you, most of you noted correctly that you should maybe use Pythagorean theorem. However, we're getting caught up in some of the algebra, and then it should be 20 squared equals 10 roots of 3 squared plus x squared, if you call this little piece x. 10 roots of 3 squared is not 30. 10 roots of 3 squared is 10 times 10, root 3 times root 3. 10 times 10 is 100. Root 3 squared is 3. 100 times 3 is 300. So you get 400 equals 300 plus x squared. X squared is 100. X, therefore, is square root of 100, or 10. And if this chunk is 10, the whole side length is twice that, which is 20. Plug those three things into our formula, and you're good to go. Rock and roll. You've got your area.
Rock and roll.
Okay. In this case, the piece to find was the side length. This was the kind of the meat of the problem. If I give you the apothem, chances are you're going to have to find the side length.
Wait, what's the final answer? Wait.
Or I could even just give you, say in this case, I could tell you, say, what the radius of this regular nonagon is. I could just tell you that from the center to a vertex is 4. And I claim that that is more than enough information for you to calculate everything you need. Specifically, we need to know the apothem length. We need to know the side length. We need to know how many sides there are. Hopefully, the n, this number of sides, is something you can always do. If you are finding the area of the regular polygon, you should at least be able to do this. Just count. Or know that a nonagon has 9 sides. Unfortunately, right now, unlike the previous one, I don't just go out and out tell you what one of these are. And this is an important piece. I don't just tell you what either one of these are. So now we're going to have to go out of our way and actually calculate. Boy, how the heck am I going to do that? If I don't tell you what one of these two are, we're going to have to take advantage of that second property of a regular polygon, which is that all internal angles are congruent. Namely, what should this internal angle be? What should angle KLJ be in my regular 9-sided polygon? Well, it should be 360 divided by 9, which is exactly 40 degrees. And if I draw the apothem, I make a right triangle. So what should this smaller piece of that angle be? If I were to say redraw this triangle, what should this angle here be then? Half of 40, which is 20 degrees. Oh boy. If I give you a right triangle and I tell you an angle and the hypotenuse, we need to know the apothem, and we need to know the side length. The apothem on our little right triangle is this length, and half of the side length is this leg over here. This is like half of the side. I think I heard someone kind of moan about how we're going to have to find those pieces. We're going to have to use trigonometric functions, trig functions. Sine, cosine, tangent. You can play all you want. So, we'll start with the apothem. I think this is the easier one. I know, folks, here is I know I have a leg. If I knew the ratio of the leg, say, to the hypotenuse, that's adjacent to this 20-degree angle, what trig function should I use? Adjacent and hypotenuse. A over h is cosine. The ka in SOHCAHTOA is cosine. So cosine of 20 degrees is equal to a over 4. A word of warning, make sure your calculators are in degree mode when you're trying to use these trig functions. You don't want to be in radian mode accidentally. So the apothem length is going to be a decimal approximation here. 4 times cosine of 20 degrees, and what did we get?
No, I did it wrong. 3.75.
Approximately 3.75. The side length, then, well, let's see, half of the side length is opposite over hypotenuse. So you could say that this quantity, or half the side length,
Wait, what is that?
over 4 is the sine.
Wait, what is tan then?
Tangent is TOA, opposite over adjacent.
Oh, yeah. Is it S?
This is half of S, or 0.5. You can call this like X and double it, like we have been.
Yeah.
The side length here is opposite over hypotenuse, or sine of 20 is this quantity over 4. We had been calling this X. If you want to continue to do that, that's fine. If you want to call this thing just like X, then this is just X over 4, find X, and then you make sure we double it, because this piece in here, once you know what X is, double it, and that'll tell you the side length. So 4 times sine of 20, what's 4 times sine of 20? Then we can calculate that. So 4 sines of 20 is 1.36. Double it is the side length. It's 2.73. From this information, we've gotten each of these. Again, this all hinged on 2 things. It hinged on us knowing that the interior angle measures are all congruent. So we need to calculate what the internal angle measure is and set up a little right triangle. Note that this angle we're using is half as big as the internal angle measure. It also hinged on you remembering your trig functions. So if you need to go back and look at section 7.5 and 7.6 in your notes, that's a good reference for you. If you don't recall sine, cosine, and tangent very well, those would be a great reference for you to go back to. Okay. And again, once you got your apothem, the side length, and how many sides, now it's a matter of plugging into our formula. The last one, folks. I know we've gone right to the edge here. I know we've gone right up to the edge here, but I want to make sure we talk about the last example. This last example I have here. There's two more on the sheet. We're going to do this. We'll end here before I kind of cut you loose. It's more than enough information to just give you the side length of one of the polygons. If I tell you the side length, we can kind of work backwards. So if I know the side length, I still in the end need to know what the apothem is, what the side length is, and how many sides. Well, in this case, of this polygon, the side length is clearly 7. We can count how many sides there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides. From here, this means the only thing that we need to calculate then is what the apothem length is. Well, to do that, we can take our polygon and let's create a little wedge that's in here. And go even further and draw in the apothem. What do we know about, what's something we could fill in on, say, if we have, working backwards, we have this right triangle. This is 90 from it being an apothem. I claim that we should know what this piece of this right triangle is. This corresponds to here, which is half of the side length, or 3.5. And you should be able to calculate what this internal angle is. We should be able to calculate what this angle is. Well, let's say 10-sided figure, so what's the whole angle measure? 360 divided by how many sides? 10. So 360 over 10 is 36. And that means this sliver has got to be half of that. So then this angle right here...
Wait, why do you have to split it in half?
Because I need to make a right triangle in order to make right triangle trig to work. In order for sine, cosine, or tangent to work, I need to have a right triangle. And what's even better, on top of that, by making this right triangle, I'm guaranteeing that the apothem that we drew, that this segment that we draw, the altitude of this triangle is actually the same as the apothem. So once I make this triangle, if I could figure out what this length is, that's all I needed. Well, this is 18 degrees. I know this is 3.5. Here's A. Oh, this is exactly the one you wanted. This is opposite over adjacent, or tangent of 18 degrees is equal to 3.5 over A. Or by solving this, multiply both sides by A, divide by tangent. A is 3.5 over tangent of 18. Come up with a number, plug it in for apothem length.
Or do you not know? So what do you do after? Oh yeah, we're just